Hello guys, today we will discuss about some general aspects on ultrafast laser processing. In my previous video I have shown that for I have shown the energy diagram for different materials uh, where the absorption of incident photon energy occurs in the linear regime, but for in laser processing is basically it's uh, is a technique, optical technique, where laser is used as an optical tool to make micro or nano fabrication in the bulk or on the surface of transparent materials, and later on that materials can be used for several purposes. For example, optical waveguides, optical resonators for sensing applications, and many others. But anyway, in order to modify any materials, what requires is the absorptions, and these absorption of what? Absorptions of incident photons. So in any transparent materials, for example glass fused silica, in order to modify the bulk of fused silica, the material has to absorbs incident photon energy non-linearly. That means multi-photon absorptions is required. So what happens in multi-photon absorption is, here you have the material, for example fused silica, having valence band and conduction band separated by a very large band gap of around 9 electron volt. So what happens when we focus such high intensity laser beam in the bulk of such materials? The material absorbs the incident photon energy non-linearly to promote a single electron from the valence band to the conduction band. So in order to absorb this electron from the valence band to the conduction band, it requires multiple photons to absorb. So this is called multi-photon absorptions, and the absorption rate is proportional to I to the power k, where I is the intensity of the laser pulse and k is basically the multi-photon absorptions orders by which the material absorbs the incident photon energy. So when such multi-photon absorptions occurs, it generates free electrons in the materials. That means it generates electron plasmas. So once the material gets ionized, it starts to modify gradually. And in order to modify a material, for example fused silica, we require the electron density, that is the plasma density, as high as greater than 10 to the power 19 per centimeter cube. So you can imagine this number is very high. So to make a single modifications by high intensity laser pulse inside the bulk of any material, we require plasma density of 10 to the power 19 per centimeter cube. Normally, in laser processing, high numerical aperture objective is used in order to tightly focus the incident laser pulse inside the bulk of the material. When we tightly focus the incident beam inside the bulk of the material, it develops plasma inside, which tends to modify the material. And this modification response depends on several factors. For example, uh, in terms of temporal control, it depends on pulse durations, the incident laser energy, and the number of incident pulses. And one more parameter I forget to mention here, which is frequency rate. which is interlinked with the number of pulses. This is all about the temporal aspects, but this modification also depends on the types of focusing optics we are using. In conventional laser processing, we normally use high numerical aperture microscope objective lens to modify any materials. And then we come to the dimension of the modifications, which is directly proportional to the incidence pulse energy and also on the number of pulses. So more you expose the materials to the incident laser pulse, the dimension of the modification will of course increase. Another important thing is the numerical aperture of the focusing optics defines the focus spot size which we require to make modifications. So higher is the numerical aperture, smaller is the focus spot size. So smaller spot size defines very tight focusing conditions where we have very high energy concentrations inside the materials. Thank you very much.